Hi there, this is Soman and you're watching the Genesis YouTube channel. Earlier, while studying Newton's law, we introduced the concept of friction. And we have seen that an object sliding across a floor with some initial velocity and no applied force comes to rest due to the force of friction. Friction depends on the type of materials in contact and is proportional to the normal force. We also discussed drag and air resistance, and we have seen that at low speeds, drag is proportional to the speed, whereas at high speeds, drag is proportional to the speed squared. Now we will introduce the forces of friction that act on fluids in motion. For example, a fluid flowing through a pipe is subject to resistance, a type of friction between the fluid and the walls. Friction also occurs between the different layers of the fluid. These resistive forces affect the way that the fluid moves through the pipe. When you pour yourself a glass of juice, the liquid flows freely and quickly. But if you pour maple syrup on your pancakes, that liquid flows slowly and sticks to the pitcher. The difference is fluid friction, both within the fluid itself and between the fluid and its surroundings. We call this property of fluids viscosity. Juice has low viscosity, whereas syrup has high viscosity. The precise definition of viscosity is based on laminar or non-turbulent flow. This figure shows how laminar and turbulent flow differ. When the flow is laminar, layers flow without mixing. When flow is turbulent, the layers mix and significant speeds occur in directions other than the overall flow direction. In laminar flow, there is no mixing between the layers, and viscosity causes drag between the layers as well as with the fixed surface. The speed near the bottom of the flow, Vb, is less than the speed near the top, Vt, because in this case, the surface of the containing vessel is at the bottom. In the second figure, an obstruction in the vessel causes turbulent flow. Turbulent flow mixes the fluid. There is more interaction, greater heating, and more resistance than in laminar flow. Turbulence is a kind of fluid flow in which layers intermix via eddies and swirls, and it has two main causes. First, any obstruction or a sharp corner, such as in a faucet, creates a turbulence by imparting velocities perpendicular to the flow. Secondly, high speeds cause turbulence. The drag between adjacent layers of fluids and between the fluid and its surroundings can form swirls and eddies if the speed is great enough. In this figure, the speed of the accelerating smoke reaches the point that it begins to swirl due to the drag between the smoke and the surrounding air. The smoke rises smoothly for a while and then begins to form swirls and eddies. The smooth flow is called laminar flow, whereas the swirls and eddies typify turbulent flow. Smoke rises more rapidly when flowing smoothly than after it becomes turbulent, suggesting that turbulence poses more resistance to flow. This figure shows how viscosity is measured for a fluid. The fluid to be measured is placed between two parallel plates. The bottom plate is held fixed while the top plate is moved to the right, dragging the fluid with it. The layer or lamina of the fluid in contact with either plate does not move relative to the plate. So the top layer moves at the speed v while the bottom layer remains at rest. Each successive layer from the top down exerts a force on the one below it, trying to drag it along, producing a continuous variation in speed from v to 0 as shown. Care is taken to ensure that the flow is laminar, that is, the layers do not mix. The motion in the figure is like a continuous shearing motion. Fluids have zero shear strength, but the rate at which they are sheared is related to the same geometrical factors A and L as is shear deformation for solids. In the diagram, the fluid is initially at rest. The layer of fluid in contact with the moving plate is accelerated and starts to move due to the internal friction between the moving plate and the fluid. The next layer is in contact with the moving layer, and since there is internal friction between the two layers, it also accelerates, and so on through the depth of the fluid. There is also internal friction between stationary plate and the lowest layer of the fluid, next to the station plate. The force is required to keep the plate moving at constant velocity due to internal friction. This force, which is required to keep the top plate moving at constant velocity v is found experimentally to depend on 4 factors. First, it is directly proportional to v. That is, until the speed is so high that turbulence occurs, then a much larger force is needed and it has a more complicated dependence on v. So here we are talking of relatively small v's. Second, the force is proportional to the area A of the plate. This relationship also seems reasonable because A is directly proportional to the amount of fluid being moved. Third, F is inversely proportional to the distance between the plates L. This relationship is also reasonable as L is like a lever arm, and greater the lever arm, less the force that is needed. Fourth, F is directly proportional to the coefficient of viscosity eta. The greater the viscosity, the greater the force required. These dependencies are combined into the equation F is equal to eta VA by L. This equation gives us a working definition of fluid viscosity, and solving for eta gives eta is equal to FL by VA. And this defines viscosity in terms of how it is measured. The SI unit of viscosity can be found from the formula, and you can easily see that it is Pascal second. Viscosity varies from one fluid to another by several orders of magnitude. As you might expect, the viscosities of gases are much less than those of liquids, but all these viscosities are mostly temperature dependent.